This is the lecture video on Chapter 7, Thermochemistry. Here we're going to be studying heat energy associated with chemical reactions like combustion and neutralization, and we're going to take a small look at physical reactions like boiling water or melting of an ice cube, just to see how heat is involved in these different reactions. Here we have the chemical reaction for most hand warmers. We have iron solid coming in contact with oxygen gas to produce iron 3 oxide. The only thing that's missing here in this equation is the heat that's being released. So throughout this chapter, as we're going through different chemical reactions, my suggestion to you is write in the word heat where it should appear in the chemical reaction. So here in this case, because heat is being produced, we're going to write it as a product. Okay. Also with these different reactions that you're going to see, we are going to revisit an idea called stoichiometry. Now, what is that? We're basically going to manipulate the amount of reactants that we have so that we can come up with different amounts of products as the reaction moves forward. Now, this is important here in real life because, well, let's say that the chemical hand warmer that you bought doesn't produce enough heat that'll make you feel comfortable. Well, you're going to have to find something that has more reactants so that it can produce more heat. So these are the types of math problems that we're going to see throughout this chapter. Before we really dive into the concepts of thermochemistry, we're going to need to understand some basic definitions. So one of them is energy, the capacity to do work. You should have heard this term already in Chemistry 101, in high school, elementary science. Okay. Work is a type of energy. If you've had physics before, you would know that it's force times distance. Heat is another form of energy, and you would see this when a hot object is in contact with a cold object. Heat is going to flow from the hot object to the cold object. So for right now, think of energy as an umbrella term. It's something that an object can possess. It can flow from one object to another. Heat and work are two subcategories, if you will, of energy. They're different types of energy that can also flow from one object to another. So when we add these three definitions with chemistry, then we have a branch of science called thermochemistry, just relating energy and chemical reactions together. If you're really good with Greek and Latin root words and their meanings, then when you come across different science terms, it'll be very easy for you to understand what they mean. So here are some more definitions. Specifically, we're going to look at different kinds of energy. So first is kinetic energy. Whenever you see K-I-N-E or K-I-N, most likely that's going to deal with motion. So kinetic energy is the energy of motion. Thermal energy, you're going to think of heat. It's also a form of kinetic energy. If you want to think of it this way, pretend that you're boiling a pot of water. Okay, you're introducing heat to that pot of water, so that's their thermal energy. And think about what's happening to those water molecules that are in the pot. Well, they're moving faster and faster, so that's where we get the kinetic energy. Potential energy is based on the position of an object. When we think of it in terms of chemistry, then we are specifically looking at the bonds that are holding the atoms together in a compound. One example that I like to give is placing a cell phone on the edge of a high shelf. That's not a very safe place to put your cell phone. It has high potential energy because it's on a high shelf. So that's something that you have to relate. If there's an object that has a high amount of potential energy, it is also considered very unstable. Now, if you take that same cell phone and put it on a very low coffee table, well, now the potential energy has been lowered. And if you lower the potential energy of an object, you're also making it more stable. Your cell phone is much safer on a low coffee table compared to a high shelf. So here we could see the different forms of energy and how they're related to each other. Like I said, with potential energy, when talking about chemical compounds, we are actually talking about the bonds, so position of electrons and the nuclei in those chemical compounds. All these different forms of energy that we have and can experience, they can change from one form to another. So electrical energy doesn't stay as electrical. Nuclear energy doesn't stay as nuclear. They can convert from one form to another. And this is where the law of conservation of energy comes in. Energy cannot be created or destroyed. This is very similar to the law of conservation of mass. In that case, mass cannot be created or destroyed. Whatever we have in the universe is it. We could just have different forms of it. So if you take a look at the picture that we have here on this slide, in part A, you could see this young lady holding down a ball against a spring. This is a type of potential energy, an energy of position, but specifically mechanical because a spring is involved. Now look what happens in part B when she lets go of the ball. The ball is now moving, so all of the mechanical potential energy has been converted to kinetic energy. Whatever amount of energy, of potential energy that was involved before she let go, got converted to kinetic energy. None of that was destroyed. So now we have to keep track of where the energy is flowing. We're saying it's going to flow into an object, out of an object. Well, what are these actual objects? We're going to have to define them. So here are a couple of more definitions that'll help us out. A system is the thing that we're looking at. It's the object that we're focusing on. It's the chemical reaction that we are observing. Now, if you look at everything else, like you don't look at the system anymore and you look at everything else that's surrounding the system, well, that's called the surroundings. Okay, so let's take a look at these definitions in a different way. So we have our system. That's the object that we're focusing on. Okay? Everything else is called the surroundings. When you add these two things together, you have the universe. So whatever is going to be exchanged between the system and surroundings, all of that is going to stay constant in the universe. So the amount of energy that we have that's going between the system and surroundings, going back and forth, all of that would stay constant based on the law of conservation of energy. All right, so now let's try to take this and put it in a real world example. Okay, so we still have our universe. our system here is our bank account. Now this is going to be a very special bank account. You could put your dollar bills, your coins, diamonds if you have it, okay? Anything of value to you, you're going to put in this bank account. What are the surroundings going to be? Well, that's going to be the bills that you have to pay. That'll be the job that's going to pay you, etc., etc. Now, how is money going to go back and forth between your bank account and your bills and your job and everywhere else? Well, there needs to be some debit and credit transactions. Okay, and again, what's being moved in these transactions? Your money. Okay. So whatever energy is going to be lost by the system, it's going to be gained by the surroundings, and vice versa. So if we take a look at the top half of this picture, we could see that the energy gauge for the system is half full, and that for the surroundings is a quarter full. Now, what happens if an energy transfer takes place? Well, now we'll take a look at the bottom half of this picture. We see now that the system energy gauge is a quarter full. It lost some energy. Now, where did that energy go? That same amount got transferred to the surroundings. Energy was lost by the system, but the amount of energy in the universe stayed the same. Okay, so if we're going to do some math problems with energy, we're going to need to take a look at some units. So here, if you haven't seen this equation before, like if you haven't taken physics before, this is the equation for kinetic energy. 1/2 mv squared. M being mass, v being velocity. These units are very specific. The mass is in kilograms. Velocity is meters per second. But because we're squaring it, it's meters squared over seconds squared. So this is the unit for energy. But a better way to look at it is for every 1 kilogram meter second over, a meter squared over second squared, all of this is equal to 1 joule. So when you see 1 joule, always think of this more complicated unit. Okay? It's very important that you remember this because in the math problems that we're going to see, you might have to convert mass, let's say. Like they might give you mass in grams, and if you need to use the joule unit, you're going to have to convert that gram to kilogram. Here are some more units that you would need to know. Okay, table 7.1 is really good to memorize. Here we go. So 1 calorie or 1 cal is equal to 4.184 joules. This number right here is going to be very important later. We'll see that in a little bit. Calorie with a big C. So when you go food shopping in your grocery store and you want to take a look at the nutrition facts that are on food packaging, like on boxes and bags and whatever, those calories that you see are the big C calorie. Okay, so 1 big C calorie is equal to 1,000 small C calories. Okay, make sure you don't get those two confused. Okay, so we're going to take a look at thermodynamics now. Thermo meaning heat, dynamics meaning change. So we're going to see how energy changes from one form to another. There are 3 different laws of thermodynamics, and the first one you already know because it is the law of conservation of energy. So whatever energy we have in the universe, remains constant. We don't get any extra energy anywhere. We're not going to lose energy. So you might have heard this before. If you're trying to design a system that produces energy, whatever energy you put into the system is the same amount that you're going to produce. You're not going to, create any magical system where you would produce more energy than you put in. Okay, so here is a different way of looking at the law of conservation of energy. If you just take a look at this first half, the left-hand side of this equation, the energy of the universe remains constant. There is no change in the amount of energy in the universe. Okay, if you take a look at the right-hand side of this equation, you're going to see that if you take the energy of the system and the surroundings together, that also doesn't change. That sum, that whatever amount that we have, that also doesn't change because the system and the surroundings is the universe. Okay, now take a look at this triangle that's in front of the energy. That is the Greek symbol delta, and that means change. So whenever you see the symbol, you're always going to think final amount minus initial amount. So internal energy is another type of energy, and specifically it looks at kinetic and potential energy that's within a system. We're only looking at the system here, not the surroundings. Okay? Internal energy is also called a state function, and that's where the final condition and the initial condition matter. The path to get to those conditions do not matter. That's what a state function is. You're only looking at the initial and the final. If you're looking at a chemical reaction, chemical equation, that's products minus reactants. The path doesn't matter. This is a very good picture to try to understand state function. Okay, you can see that we have a mountain here. It looks like a triangle. It looks like the Greek letter delta for change. So again, a state function, it doesn't matter what path you take. It's just the initial position or initial condition and final condition. So let's say that you needed to reach the top of this mountain and you have two different paths that you could take. If you're not so physically fit, you might want to take path A. Yeah, it's going to take a longer time for you to get up there because it's 12 miles long, but it's an easier path to get to the top. Or you could take path B if you're more physically fit. The path is shorter, a shorter distance, but it is steeper. You going up there is it's gonna be harder for you to do. But now take a look at the altitude. The altitude is just a change in position. Okay, initially you were at 0 feet. When you reach to the top, you're at 10,000 feet. This is our final position here. So no matter which path you take, the altitude of that mountain will still be 10,000 feet. That is what a state function is. Just the difference in final and initial values, and you don't pay attention to the path. Let's take a look at some energy diagrams to see how the change in energy can differ depending on the internal energy of products and reactants. So here we have a carbon solid reacting with oxygen gas to form carbon dioxide gas. For This slide, I personally would like to put numbers so that I can understand the slide better. So on the reactant side, let's just say that these two reactants together are equal to 10 joules. On the product side, let's say that the carbon dioxide has 3 joules of energy. There we go. All right. So here we have the reactants having a higher internal energy than the products. All right, so now it's also saying that the change in energy will be negative. All right, so what does change mean? Products minus reactants, final minus initial. So it's 3 minus 10 joules. That'll be negative 7. Okay, so the change in energy for this reaction, going from left to right, would be negative 7. Now what if we flip the equation around? Now carbon dioxide is our reactant. Well, we're still going to make it 3 joules. 3 joules. And our carbon and our O2 is going to be 10 joules. All right. So now our reactants have a lower internal energy compared to the products. So the change in energy will be positive. So that's products minus reactants. 10 joules minus 3 joules would be positive 7 joules. All right, sticking with this same example, we're forming carbon dioxide. So our reactants, they're going to have an energy of 10 joules. Carbon dioxide would be 3 joules. Here's our little energy diagram. Carbon dioxide is lower because we're saying that it has 3 joules, and carbon and oxygen gas together would have 10 joules. Okay, if this reaction is going to go forward, going from left to right, then the internal energy is going to go down. We're going from 10 joules down to 3 joules. Well, what's happening with those 7 joules of energy? It's being released. It's being released by the reaction. And here we're saying that the reaction is the system. So if the system is releasing energy, what's going to absorb the energy? The surroundings. That energy has to go somewhere. If it's being released by the system, then it's going to be absorbed by the surroundings. So when you take a look at this relationship here, delta E reaction, that's also delta E system. If delta E reaction is releasing energy, then the surroundings is going to absorb that same amount of energy. Okay, so now let's flip the equation again. Our carbon dioxide is our reactant now. It's got 3 joules of energy, so here it is towards the bottom of our energy diagram. Our carbon and our O2 gas, they would have 10 joules of energy, just like before. But now, look what happens when we're trying to go from left to right as we proceed through this chemical reaction. Energy is going to be needed so that we can increase the amount of internal energy in the system. Okay, energy needs to be absorbed by the reaction. Well, where is this extra energy coming from? It's coming from the surroundings. If you want to think of it this way, the surroundings is going to release heat and the system is going to absorb that same amount of heat. Okay? So now take a look at this relationship here. Our delta E reaction is positive now compared to the delta E of surroundings, which is negative. So like I was saying before, if you want to think of it this way, pretend that the surroundings is releasing the energy to the system, to the reaction, so that the internal energy can increase, and so that we could produce the carbon solid and oxygen gas. Let's try out this question here. Again, we have energy gauges for system and surroundings. We could see that the chemical system is 3/4 full, while the surroundings is only 1/4 full. We got our three choices here. Which one shows an energy exchange in which delta E system is negative? Which one shows an energy exchange in which delta E system is negative? So pause the video, take a moment, figure out what's going on, look back at the other slides so that you know which signs deal with what situation. And when you're ready for the answer, go ahead and press play. Okay, so the answer to this is letter A. For delta E system to be negative, the system has to lose energy. So we have to find the choice that's less than 3/4 full. Okay, so that would be letter A and letter B. But look how letter A and B changed. It went down a quarter. So if the chemical system lost a quarter energy, then the surroundings must have gained that same amount of energy. The only one that works is letter A. With letter B, it looks like that amount of energy was destroyed because we don't see any gain with the surroundings. Letter C, it looks like the chemical system gained energy. So in this case, delta E system would be positive. All right. So, I mean, technically, like what's happening in letter C is true in terms of conservation of energy, because if the system gained energy, then the surroundings must have lost energy, and that's what it looks like it happened. But it's incorrect because here for letter C, the delta E system is positive. We're looking for something that's negative. Let's review a little bit. Heat and work are different forms of energy. And these two things can be exchanged between the system and surroundings. What you have to take note is that Q, heat, and W, work, these two are not state functions. You don't see a delta symbol in front of these two variables. Okay? So when you see Q and W, or heat and work, you have to remember that the path matters for these two. Okay? Delta E, or internal energy, you just have to pay attention to the final and initial conditions. All right, so now figuring out positive signs and negative signs for these three variables. Table 7.3 shows you the sign conventions for Q, W, and delta E. And what you're going to notice is that it's all the signs are all based on the system. That's what we're focusing on. So let's take a look at what we're doing to the system. Okay. Let's say that you have an ice cube in your hand and the ice cube is melting. The ice cube, we'll say, is the system. And it's melting because heat is flowing into it. So there, the system is gaining heat, it's gaining thermal energy, so the sign for Q is positive. Now for work, pretend that you're pushing a box across the room, and the box is the system. Well, you are doing work on the system. You are pushing the box. So the sign for W in that case would be positive. Okay. Now, when you add these two values together, and in considering the signs for the two values, the sign for delta E will tell you how energy is flowing between the system and the surroundings. So here, heat and work, forms of energy, they're going to be exchanged between system and surroundings. If heat is going into the system, if work is being done on the system, then these values are going to be positive. If heat is being taken away from the system and going to surroundings, or if the system is doing work on the surroundings, then Q and W are going to be negative values. The next several slides show very good examples of the conservation of energy and how Q and W can have different values, but the overall internal energy, the delta E, would stay the same. So you're going to see two examples of it, and we're going to be using a pool table. And for those of you that don't know how to play pool, the basic idea is this. You're going to take a stick and you're going to use it to hit this white ball, or this, what they call a cue ball. You're going to hit it so that it hits a colored ball, and you want the colored ball to fall into one of these 6 holes. Now in our first example, we're going to have a very good pool table. This green surface right here is very smooth. So there's not going to be a lot of friction as this white ball moves across the table. Okay, so now, what is the system here? The system is this white ball that we're going to hit. Okay. Initially, it's going to have a kinetic energy of 5.0 joules. When it hits the purple ball, it's going to stop because all the kinetic energy it had is going to transfer to the purple ball. So what's the delta E value for this white ball? Remember, delta, you're going to do final minus initial. Kinetic energy final, it stops moving, so it has 0 joules of kinetic energy. Initially, we said that it had 5.0 joules, so when we subtract everything out, our delta E for the white ball is negative 5.0 joules. Okay, let's take a look at our pictures now. As the white ball moves across the pool table, heat is lost because of friction. How much heat? 0.5 joules. Okay, whatever was left over, that's going to be used to push and move the purple ball. All right, so now let's put everything together. We know that Q is negative 0.5 joules because that was the energy that was lost as heat. Okay, heat is Q, energy was lost. That's why our value for Q is negative. All right, now the work that's being done. The work that's being done is by the system, by the white ball. So for our W, we have a negative 4.5 joules because that's the amount of energy that was left over. When we put it into our equation, look at our delta E. It's still negative 5.0 joules, just like before. Okay, now we're using a pool table that's not the best quality. It's a bit rougher. The situation is going to be the same. We're going to hit this white ball so that the purple ball moves. Now take a look at the amount of heat lost. Look at our Q value now. It's going to be negative 3.0 joules. Okay, because this is a rougher table, more heat is going to be lost due to friction. Now look at the amount of kinetic energy that's left over. Look at how much energy is going to be used to move the purple ball. It's only going to be 2.0 joules. Okay? Now let's do our calculations for delta E. Again, kinetic energy final minus kinetic energy initial. Same as before. We end up with negative 5.0 joules. This time around, we have different values for W and for Q. But if we plug it into our equation, delta E equals Q plus W, we're still going to end up with negative 5.0 joules. So in these two examples, it doesn't matter what the values are for Q and W. If one of them increases, so in this case for Q in the rougher table example, the second example, the Q got larger. So that means the value for W in that second example is going to have to be a smaller number. In the end, we're going to see, when we did see, that delta E for both situations was the same. Let's take a look at this question here. Which energy exchange is best classified as work? So read these three sentences very carefully. We know that energy can be broken down into work and heat. So read through these, pause the video, make your choice, and then when you're ready, click play. Okay, so our answer here is letter B. A metal cylinder is rolled up a ramp. The cylinder is the system, so you could picture yourself applying work onto this system right here. Okay, there's no indication of heat being involved, but let's take a look at options A and C. In A, an ice cube is melting, so heat is being introduced to the system so that the ice cube can melt. Letter C, steam condenses on skin. So with the steam, heat is being released in order to become liquid onto the skin. So again, the answer here is letter B. Here is a math problem that I would like for you to try out. We could actually do this together, so let's take a look at what's going on here. We have a potato cannon. So we're stuffing a potato in this cannon. We're going to fire it. There has to be some kind of fuel in order to do that. So let's see. The cannon emits heat to the surroundings. If the burning of the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is E for the burning of the fuel? Okay, so just like with the last question in the last slide, it's important for you to figure out what the system is. And here they're pretty much telling you. They're saying what is the energy for the burning of the fuel. So the burning of the fuel, the combustion reaction, is the system. All right, so let me give you a few moments. Just press pause, try to work this out yourself, and when you're ready, click play. Okay, so we said that the combustion reaction is the system. So we're going to use this equation, delta E equals Q plus W. Our Q here is the 1,422 joules. It has to be negative because heat is being produced. Heat is being released by the system. That's why it's negative. Our value for work is also negative because our system is doing the work. Okay, the burning of the fuel performs work on the potato. The potato is part of the surroundings. Okay, so all right, we got our two values with appropriate signs. So when you do the arithmetic, our final answer is negative 2,277 joules. Here's another problem involving energy, work, and heat. So we have a cylinder and piston assembly, which they define as the system. Okay, when the cylinder expands, it's doing work on the surroundings. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of E? Okay, so again, take a moment, press pause, figure out which value is Q, which one's W, and their signs. When you're ready for the answer, click play. Okay, so here's the work for this problem. The system is absorbing 559 joules of heat, so that's why our Q here is positive. The system is also doing the work, and that gives our 488 a negative value. Now when you add these terms together, you should get positive 71 joules. Now we're going to take a closer look at heat. At this point, you should know that heat is what's being exchanged between the system and surroundings. Specifically, it's thermal energy. And usually that happens when there's a difference in temperature in the system and the surroundings. For us to figure out how much thermal energy a system has, we have to take its temperature. So when heat is flowing from a hot object to a cold object, we could take the temperatures of both of those objects and monitor the heat exchange between the two. Now, at some point, those two objects are going to reach the same temperature. And when they do, we say that they've reached thermal equilibrium. So when you heat anything up, the temperature of that object would increase. But if you have two different objects absorbing the same amount of heat, they could end up with different temperatures. And that's because it takes a certain amount of heat to increase the temperature of a substance by 1 degree. So when we try to relate heat and increasing the temperature of an object, what we have is called heat capacity. If you just do a little bit of math, you'd be able to see that if a substance has a very large heat capacity, so letter C here, if it's very large, then the change in temperature is going to be very small for a given amount of heat. So let's say that we have object A, and it has a heat capacity of 2, and it's going to absorb 100 joules of heat. Well, what would be the temperature difference after the heat was exchanged? 50 degrees. All right. Well, now let's take a look at object B that has a larger heat capacity. We're still working with 100 joules. Object B is going to absorb 100 joules of heat. The heat capacity would be 25. Now look at the temperature difference. It got smaller. So again, if you're dealing with a very large heat capacity, a substance with a large heat capacity, the temperature difference after the heat has been exchanged would be very small. A good example of that would be picturing yourself on the beach on a hot day. If you ever experienced this before, the next slide would make a lot of sense to you. So here you are at the beach, very hot day. Let's say that you forgot your flip-flops and you're walking on the sand. How would the sand feel when you touch it with your feet? It's probably going to be pretty hot, especially on a very sunny day. You're probably not going to walk on the sand. You'll probably run on the sand, try to get to the water. Why? How would the water feel now? It's probably going to feel very cold. Now, why is that? The water and the sand are both under the sun. The sun's not going to discriminate. It'll give off a certain amount of heat, and the water and the sand are going to absorb that heat. But why is it that the sand is going to feel so much hotter than the water? So like we were mentioning before, substances would have different heat capacities. They'll absorb different amounts of heat before their temperature would increase by 1 degree. So here we are with the sand and the water. Let's say that they both try to absorb 1,000 joules of heat and we have the same amount of sand and water. The temperature of the sand is going to increase by 12 degrees, but if you look at water, it's only going to increase by 2.4 degrees. Now, which one is going to have the smaller heat capacity? Well, that'll be the sand because it has the higher delta T. It has the higher temperature change. Okay, so that's one factor affecting heat capacity. The other factor depends on the actual amount of matter that we have. So if we're sticking with water, we're going to need more heat to raise the temperature of water by 1 degree if we have more water to begin with. So if we have two different beakers of water, one with 200 grams, the other with 100 grams, we're going to need more heat to actually raise the temperature of the 200 grams of water. Okay, so here's another equation regarding heat, regarding Q. It looks very similar to the heat capacity equation, Q equals C times delta T, except now we have mass, and our mass is in grams. So because we have this extra variable here, we don't have the same letter C. Now this is called specific heat capacity. It is specific to a certain mass of our substance. Okay. Also take note of the unit for specific heat capacity. Now it's joules over grams times Celsius, which is regular heat capacity. It was joules over Celsius. So again, these two equations are very similar, except this one now deals with mass, and this is for specific heat capacity. Here are some examples of common substances and their specific heats. Okay, you can see that we have water here at 4.18 joules over gram times Celsius, and we also have sand, 0.84. Now again, going back to our sunny day at the beach, which substance, sand or water, would have the smaller specific heat? Obviously here it's the sand, we could see it in the table, but we know that the sand would get hotter compared to the water. So whichever one has the greater temperature difference would have the smaller specific heat capacity. Okay, so all of these values, they're based on mass. There's another set of values called molar heat capacities, and that's based on 1 mole of a substance instead of 1 gram. Okay, so again, take a look at table 7.4. You don't have to memorize all of this. Really, the value you should memorize is that of water. But when you take a look at this table, you should know which substance would have the greatest temperature difference and which ones would have the smallest temperature difference. What this slide is saying is that because of moisture in the air, water in the air, you won't experience a huge temperature difference going from morning to night if you live in coastal areas. And that's because of the large specific heat of water. It can absorb a lot of heat energy. Now, if you compare that to living in the desert, where there's practically no moisture in the air, then it's almost like you have to dress for 2 different seasons going from morning to night. Okay, when the sun is out, you'll probably be in shorts, a tank top, okay, probably like sweating all the time. And when the sun sets, I don't know, you might need a winter jacket or something because the temperature would fall drastically because there is no moisture in the air. Okay, so here's our next question. Pretend that you are cold weather camping and you need something to keep you warm when you're sleeping in your sleeping bag. You have a large water jug and you have a rock. Let's just say it's made out of granite. They both weigh the same and you're heating them up next to the fire. At some point, they both reach the same final temperature, 38 degrees Celsius. Which one of these items would you bring to your sleeping bag so that you stay warm all night, and why? Take a moment to figure it out, press pause, figure things out for yourself, and when you're ready, click play. Okay, so the answer here is letter A. You would pick the water because it would have absorbed a lot of heat compared to the rock. Okay, if this is a little too confusing, then just go right ahead and put some numbers in, see if it makes sense that way. Okay, so we're gonna warm up the rock and the water jug to 38 degrees Celsius. Which one are you gonna bring to your sleeping bag so that you could keep warm at night? So we're gonna need to use Q equals MCAT to figure out how much heat each object is going to retain. Okay, we're going to have to make one assumption here. We already know that the mass of the water and the mass of the rock are going to be the same, 100 grams. Our final temperature would be 38 degrees for both. And I'm just going to go ahead and say that initially both objects start off at 0 degrees Celsius, just to make the math easier. The specific heat of water is going to be 4.184 joules per gram Celsius. And when you punch everything into the calculator, you would get 15,884 joules. Okay, now do the same thing for the granite. The only difference here is that the specific heat for the granite is 0.79 joules per gram Celsius. Now take a look at the amount of heat it would retain. It's not as much as the water, so I would bring the water jug with me in my sleeping bag so that I could stay warm throughout the night. Okay, so let's try the Q equals MCAT equation. Here we have a penny that was found in the snow. We need to know how much heat is absorbed by the penny as it warms from negative 8.0 degrees Celsius to 37.0 degrees Celsius. We're going to assume that the penny is pure copper and has a mass of 3.10 grams. Okay, so we have our table of common substances and their specific heat capacities. First thing that you need to do is to write out all the variables that are given to you and their values. If you don't know their values, then you just put a question mark next to that variable. And I highly suggest that you do this every time you come across a math problem. In this chapter, you're going to have to memorize and understand a whole bunch of equations. For Q, you've already seen two equations for Q. Q equals MCAT and Q equals C times delta T. Okay, so I can understand you being confused with which equation to use, but here you could see that we have mass, so that's where you would know to use the Q equals MCAT equation. Okay, so that's the Q equation that we're going to use. We have our specific heat of the copper, so let's start working it out. Okay, so we're simply just going to plug in our values to solve for Q. For delta T, you need to remember that it's final minus initial. Always final minus initial. And here, because we know that the temperature increased, we should have a positive value for delta T. Okay, so now when we plug everything else in, we should have, in the end, if you punch in the values correctly in your calculator, you should get 53.7 joules. Okay, and again, this should make sense. The sign of Q is positive because heat is being absorbed by the penny. Okay, the penny is the system. Here's another problem for you to work out. It's a little bit different, but you're still going to be using the same equation. A student found a gold-colored rock, and she's trying to figure out if it actually is gold. The mass of that rock is 4.7 grams. It absorbed 57.2 joules of heat. The temperature of the rock changed from 25 degrees Celsius to 57 degrees Celsius. She needs to figure out the specific heat capacity of this gold-colored rock. Okay, so that's what you have to figure out. First, use Q equals MCAT, figure out the specific heat capacity of the rock, and then compare that to gold. If you come up with the same value as what's in table 7.4, then you do have gold. So go ahead and pause this video, work this out yourself, and when you're ready for the answer, press play. Okay, so here's the work for this problem. Again, we're going to use Q equals MCAT. We're going to rearrange the variables so that we can solve for specific heat capacity. Okay, we plug in our values. Our 32 degrees Celsius, that was our delta T when we did final minus initial. And so we come up with 0.380 joules per gram Celsius. Now, is this shiny gold-colored rock actually gold? No, it is not, because if we take a look at our table, our specific heat capacity for gold is supposed to be 0.128. So this rock is not pure gold. Okay, so you can use specific heat capacity as an identifying factor for different substances. Here's another problem for you to try out. Here you have an aluminum block that weighs 55.0 grams. It's initially at 27.5 degrees Celsius and absorbs 725 joules of heat. What is the final temperature of aluminum? So please pause this. Take some time to figure it out. You have table 7.4. And when you're ready, click play. Okay, so again, we're using Q equals MCAT. We have all of our values, but we're trying to figure out the final temperature. Okay, so there is a little bit more math involved, but this is algebra, so this shouldn't be too much of a problem for you. Okay, so we're going to multiply the 55.0 grams by 0.903 to get the 49.665. Now we're going to take this factor and divide it on both sides so that we can get rid of the 49.665 on the right-hand side of the equal to sign. Okay, now we're at this line of calculation. All right, we combine the like terms, which is degrees Celsius, to get 42.1 degrees Celsius. Let's take a look at what happens when two objects at different temperatures come in contact with each other. Here in our picture, let's say that our metal is our system and it's hotter than the water. Well, heat is going to flow from the metal to the water. The water is going to absorb whatever heat is going to be released from the metal. And heat is going to keep flowing until both the metal and the water reach the same final temperature. Okay, until they reach thermal equilibrium. Now, the amount of heat that's being lost by the metal, it's going to be the same amount that's going to be absorbed by the water. Okay, so the delta T for the metal and for the water is going to depend on several things. One would be the mass of the metal, another would be the mass of the water, and also we have to take a look at the specific heats for the metal and for the water. So whenever we have this energy transfer, this thermal energy transfer between a hot object and a cold object, we would need to write out this relationship. Okay, in this case it's Q metal equal negative Q water. Or generally speaking, you could say QA is equal to negative QB. whatever heat, the amount of heat that's going to be released by one object is going to be absorbed by the other object. Okay? We could also expand this relationship. We know Q is equal to mcat when we're dealing with specific heat capacity. So for QA equal negative QB, we can expand the Q's to mcat. One thing you have to notice here is the negative sign. Whatever sign, wherever the negative sign is, you always have to follow through in the expansion of Q. Okay, and it doesn't matter which side you put the negative sign, as long as it's there in this relationship. Okay, so here I'm going to show you why it doesn't matter where you put the negative sign. It's fine if you want to put it on the left-hand side. It really doesn't matter. So here we have a piece of metal that loses 5 joules of heat in a beaker of water. How much heat does the water gain? Okay, so we have a hot object coming in contact with a cold object. So we have QA equals negative QB. In this case, QM equal negative Q water. We could also say negative QM equals Q water. All right, so now on the left-hand side, we know that the metal loses 5 joules of heat. So for QM, we're putting in negative 5 joules. And that is equal to negative QW. Well, we don't want negative QW, we just want regular QW. How much heat does the water gain? Okay, so that variable has to be just a positive, it cannot be negative, that's not the same thing. So we have to change the signs. They'll both be positive now, so QW would be positive 5 joules. All right, so now let's take a look at the right-hand side. We have negative QM equal QW. Okay, same deal with Q metal. It's losing 5 joules of heat, but here we're putting the negative sign in front of QM. So we have negative 5 joules equals QW. Well, a negative times a negative is a positive, so we end up with positive 5 joules for QW. So you can see it doesn't matter where you put the negative sign. In the end, you'll come up with the same answer. Okay, so this question tests your understanding of the Q equals mcat equation and heat transfer. So here we have two substances, A and B. They're initially at different temperatures and they come in contact with each other. They reach the same final temperature. The mass of substance A is twice the mass of B. The specific heat capacity of B is twice that of A. Which out of these three statements is true about the final temperature of the two substances once thermal equilibrium is reached? So take a moment, pause the video, see if you're able to figure this out yourself, and once you're ready for the answer, click play. Okay, so the answer here is letter C. Based on what was given to us about the mass and the masses and the specific heats, the final temperature is going to be between the initial temperatures of A and B. So for me, I needed to work it out. I needed to make up numbers, but it had to make sense based on what was given in order to figure out what the answer is. Okay, so here's what's given to us. we know what our masses are supposed to be for substances A and B, and also the specific heat capacities. So here's our relationship. QA is equal to negative QB. We need to figure out the final temperature. So we have to expand the Q's into MCATs, but we also cannot forget the negative sign. Okay, so here we go. Taking a look at the masses, we know that substance A should be twice the mass of substance B. All right, so I just picked very small numbers. So if the mass of A is 4 grams, then the mass of B would have to be 2 grams. For specific heat capacity, substance B would be twice the specific heat capacity of A. So for B, I picked 10. So that means for the specific heat capacity of A, it would have to be 5. Okay. TF is what we're looking for, and the initial temperatures, I picked 0 for substance A and 30 degrees for B. Okay, so now let's simplify this so that we could figure out final temperature. I know that we could just cross out the masses and the specific heat capacities, because if you multiply the coefficients here, it'll be 20, and then we would get 20 over here also. We could also cancel out the units. They're the same on both sides. I do that just to make the math easier, so that in the end, well, almost at the end, we're left with just TF and temperature. So now we'll distribute the negative sign to what's in the parentheses. So we're left with 2TF. Okay, we're adding these TFs together to get 2TF equals 30 degrees Celsius. And our final temperature is 15 degrees Celsius. And that corresponds to our correct answer. It is halfway between our initial temperatures of our substances. Okay, so here we have another problem, another word problem dealing with Q equals MCAT and heat transfer. We have an aluminum cube that weighs 32.5 grams, initially at 45.8 degrees Celsius, and it was submerged in water that has a temperature of 15.4 degrees Celsius and has a mass of 105.3 grams. What is the final temperature of both substances at thermal equilibrium? Okay, so this is very similar to the last problem that we saw. As usual, we write out our variables and any values that are given. We know we're using Q equals MCAT. We have to figure out the final temperature for both substances. Okay, remember with heat transfer, we're dealing with QA equals negative QB, or in this case, Q aluminum equals negative Q water. Okay, we're going to have to expand the Q's into MCAT. Don't forget about the negative sign on one side of the equal to sign. At some point, we're going to have delta T's for both substances and a constant on one side. Okay, this is going to be very important because the calculation is going to look a little bit difficult to understand, but we'll go through everything step by step. Okay, you should know the specific heat for water already, and here is the specific heat for aluminum, 0.903 joules per gram Celsius. Okay, here we go. we have our relationship to start off with. Q aluminum is equal to negative Q water. We expand that, remembering the negative sign. Okay, we fill in our values. We do not want to expand delta T yet. We'll see if we could simplify our equation a little bit before we expand to figure out delta T. Okay, so here at the end of this calculation that I'm showing you, we have delta T aluminum equals our constant that I pointed out in the last slide, negative 14.998 times delta T of water. Okay, now we can expand that line of calculation so that we could figure out the final temperature. Okay, here going from the second to last line to the next line, we would have to distribute this constant into the terms in the parentheses. Okay. Also, this initial temperature for aluminum was moved to the other side. So before it was a negative initial temperature for aluminum, now it's positive. Okay, we start to combine similar terms. So this negative 14.998 TF was moved to the other side of the equal to sign, so now it's positive. Now both of these terms are added together. Some students would get confused going from the 14 to the 15. We'll just pretend that this TF here has a 1 in front of it. So it's like you're adding 1 plus 14.998 to get 15.998. Okay. Now we divide both sides by 15.998 so that we could just get regular TF on one side of the equal to sign. Okay. Now we can plug in our initial temperatures and do some arithmetic to get 17.3 degrees Celsius as our final temperature. Here's another problem for you to try out. You have a copper block now of unknown mass. It has initial temperature of 65.4 degrees Celsius. The copper is dropped into a beaker of water, 95.7 grams, with initial temperature of 22.7 degrees Celsius. The final temperature for both objects ends up being 24.2 degrees Celsius. What is the mass of the copper block? Okay. So pause the video. Please take the time to work this out yourself. When you're ready to see the calculation and the final answer, click play. Okay, so we're going to be using Qm equals negative Qw. We're going to have to expand it so that we can figure out the mass of the metal. Okay, and always do not forget the negative sign on one side of the equation. Okay, we move the variables over so that we can isolate the mass of the metal. We plug in all our values. Again, make sure that you know the specific heat of water. All the other specific heats, we will give you those values unless you actually have to solve for it. So if you plug everything into the calculator properly, you should get 37.83 grams of copper as your final answer. Okay, so now let's take a look at W. So in our situation here, we have a gas in a piston, and it is working against the surroundings. So our gas is our system. Okay. Our new equation here for W is W equals negative P times delta V. Okay, so when the gas is expanding against the surroundings, against an external pressure, then delta V is going to be positive. We know that when the system is doing work, that value is going to be negative. So to reflect that, we have to have our negative sign here in the equation. Okay, so another thing that you have to note is that the unit for pressure is atmosphere, and the unit for volume is liter. So in order to incorporate W with our delta E equals Q plus W equation and any other energy equation, we're going to have to change this unit. We're going to have to convert this unit, ATM times liter, to joule. So make sure that you memorize this conversion factor here. For every 1 ATM liter, we would have 101.3 joules. So let's try this one out. We have a cylinder within a piston, and it expands from a volume of 1.00 liters to 2.00 liters against an external pressure of 1.00 atm. How much work in joules was done by the expansion? Okay, so our answer here is negative 101 joules. Now hopefully you did some calculations here before you moved along with the video. So you would need the work equation with negative P delta V. We plug in our values and we end up with negative 1.00 atm times liters. But we need our answer in joules, so we have to have our conversion factor. When you calculate everything, you should end up with negative 101.3 joules, and the closest answer to that is letter D. Here's our first math problem dealing with the pressure volume equation for work. So we're trying to inflate a balloon. Okay, the volume is going to increase from 0.100 liters to 1.85 liters against an external pressure of 1.00 atm. How much work is done in joules? Okay, so as usual, write out all the variables and the values. We're trying to figure out work, so that's our unknown. We're going to use our brand new equation for work. Work equals negative P delta V. Okay, so change in volume is always final minus initial volume. We plug in our values. So work we have here is negative 1.75 liters times atmosphere, but we have to convert that to joules because that's what the question wanted. So we have our conversion factor here, and we end up with negative 177 joules. Okay, and this should make sense because the system is doing work on the surroundings. So our sign here for work is going to be negative. Here's another problem for you to try out. We have a cylinder equipped with a piston and it expands against an external pressure of 1.58 atmospheres. The initial volume is 0.485 liters. Final volume, 1.245 liters. How much work in joules is done? So please pause this, work everything out, and when you're ready for the calculations and the answer, click play. Okay, so here's the work for this problem. We are dealing with the negative P delta V equation for work. So our answer in liters times atmospheres is negative 1.2008. Now we're going to have to convert this to joules, and we end up with negative 122 joules. Here's our next problem. We have fuel burning in a cylinder equipped with a piston, so the volume is going to expand from 0.255 liters to 1.45 liters against an external pressure of 1.02 atmospheres. 875 joules is emitted as heat because we are combusting the fuel. What is delta E for the burning of the fuel? Okay, so there's an extra step here that you have to do. You have all the equations you need at this point to figure out delta E. So again, click pause to try all this out. And when you're ready for the work and the answer, press play. Okay, so we're going to figure out the work value. So we plug in the values that were given to us in the problem, and we end up with negative 1.2189 atmospheres times liters. And we have to convert that to joules, so we end up with negative 123.475 joules. Now, this is not our final answer. That's why I have all these significant digits for our joule answer. We have to figure out delta E. We only have work. So we're going to need a delta E equation involving Q plus W. Heat is released, so that's why we have a negative sign in front of the 875 joules. We already know that our system was doing work, so that's why we have a negative value for W. And our final answer is, for delta E, is negative 998 joules. So now we have equations for Q and W. And we're taking a look at our picture again with energy being exchanged between system and surroundings. If heat is being applied to the system or if work is being done on the system, then those values are going to be positive. If the system is going to release heat or if the system is going to do work, then those values are going to be negative. Now we could take all these equations and apply it to a branch of chemistry called calorimetry, and that is measuring. It's measuring the heat involved in a chemical reaction. So to measure delta E, it's best if we do that at constant volume. Okay, so don't forget, W is equal to negative P times delta V. If we make delta V 0, meaning the volume is going to be constant, then that means work is going to be 0. So we just simplified our relationship here. Whatever heat is involved in the system, that's also going to be the delta E for the system. Okay. One problem that we have, though, is we can't directly measure Q system. We'd have to take the temperature of the surroundings. So this is where QA is equal to negative QB. We'd have to use that relationship. So in order to do that, we'd have to use a device called a bomb calorimeter. So it's just an insulated container filled with water, and inside is where the reaction would take place. And again, the reaction is our system. Everything else is going to be the surroundings, and the calorimeter is part of those surroundings. So this is just an expansion of QA equals negative QB relationship. Here's a very nice picture of a bomb calorimeter. Again, it is a sealed container filled with water. Inside, this is where the reaction would take place. So if heat is going to be released, it's going to be transferred to the water. And here we have a thermometer that would monitor the temperature change. Okay. The equation that you would need to use is something that you've seen already. This is just regular heat capacity. Okay, Q-cal, cal for calorimeter, Q-cal is equal to the heat capacity of the calorimeter times delta T. Okay, our unit changed a little bit. It's kilojoules now, kilojoules per degree Celsius. So be mindful of that. You might have to do some unit conversions when working out problems like these. Okay, so let's try out a problem together. We have 1.010 grams of sucrose undergoing combustion in a bomb calorimeter. The temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. Find E reaction for the combustion of sucrose in kilojoules per mole of sucrose. They give us the heat capacity of the bomb calorimeter. Okay, so let's take a look at a couple of things here. The temperature rises, so that should tell you that heat is being released as the reaction takes place. Heat is being released, so that means the temperature of the bomb calorimeter is absorbing that heat, hence the increase in temperature. Also, the unit for E reaction is given to us. Usually it's just joules or kilojoules, but here specifically they're telling you it should be kilojoules per mole. So that means we'd have to convert our grams of sucrose to moles of sucrose at some point. Here are our given values. We have to figure out delta E reaction. So we would need Q-cal equals C-cal times delta T. Okay. Heat is being transferred from the reaction to the calorimeter, so we would need QA equals negative QB, that relationship. Also, this is what you would need to calculate delta E for the reaction, our final answer. We would need the Q reaction and then the moles of sucrose as our denominator. And here's the molar mass for it, 342.3 grams per mole. Okay, so we're going to start looking at the work. Delta T, again, always final minus initial. We see that it's a positive value, so that means that heat was released by the reaction and it was absorbed by the calorimeter. Okay, now we use our Q-cal equation. Again, our Q-cal is positive. That means that it absorbed heat. But we want Q reaction. We want Q reaction. So we're going to have to negate our previous answer. And so now we have negative 16.7 kilojoules. This tells us, this negative sign, tells us that heat was released by the reaction. Okay, so now this looks complicated, but what you're really doing here is taking the Q reaction and dividing it by the moles of sucrose. So if you take a close look at the denominator here, what they're doing is just converting grams of sucrose to moles of sucrose. And so what you're left with is negative 5.66 times 10 to the third kilojoules per mole of sucrose. Okay, so this answer should make sense. The sign is negative, so that should tell you that energy was being released during the combustion reaction. Okay, so here's another problem that I would like for you to try. We have liquid hexane, 1.550 grams of it, and it undergoes combustion in a bomb calorimeter. The temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find the delta E reaction in kilojoules per mole of hexane. The heat capacity for the bomb calorimeter is 5.73 kilojoules per degree Celsius. And we have the molar mass for liquid hexane. Okay, so this problem is very similar to the last one. So please click pause, work this out yourself, practice, practice, practice. When you're ready to look at the work and the answer, click play. Okay, so here's the equation that we would need. Q calorimeter equals C calorimeter times delta T. We plug in the values that were given to us. We end up with Q cal being 70.2498 kilojoules. But we need Q reaction in order to figure out delta E reaction. So we're going to have to negate our previous value so that we get negative 70.2498 kilojoules. Next, we're going to convert our grams of hexane to moles. Then we're going to take our two answers and divide them out to get delta E reaction. Okay, so here's our final answer. Negative 3.91 times 10 to the third kilojoules per mole. Okay, here's another one. We have the combustion of toluene and the delta E for the reaction. They give us delta E now. Is negative 3.91 times 10 to the third kilojoules per mole. When 1.55 grams of toluene undergoes combustion, the temperature rises from 23.12 degrees Celsius to 33.57 degrees Celsius. Find the heat capacity of the bomb calorimeter, and they give us the molar mass for toluene. Okay, so now here, this time, it looks like you're going to be using the same equations, but you're going to be working backwards. You have to find the heat capacity of the bomb calorimeter now. Okay, so please click pause to work it out, and when you're ready, click play. Okay, so here we go. We're going to figure out how many moles of toluene we have first. So we take the mass of our sample and divide it by the molar mass of toluene so that we get 0.016823 moles of toluene. Okay, now we use our delta E reaction equation so that we could figure out Q reaction. We need to move the variables around a little bit, so we're going to multiply the moles of toluene by our delta E that was given to us, so that we get, oh, here we go, negative 65.7779 kilojoules. Okay, we need Qcal this time. So we're going to negate our answer to get positive 65.7779 kilojoules. Now we use our Qcal equation to figure out the heat capacity for the bomb calorimeter. So we take our previous answer and divide it by delta T, and we end up getting 4.55 kilojoules per degree Celsius. Another thermodynamic entity that we're going to be looking at is enthalpy, and that's designated with the letter H, and that's the sum of the internal energy and the product of pressure and volume. Okay, it's also a state function, so you'll see it with the delta symbol, delta H, as we normally call it. Now, if this reaction happens at constant pressure, then we have our equation for work again. Okay, P times delta V. When this happens, we could cross out the W's in our equation, and so we're just left with delta H reaction equaling to Q reaction. But remember, it has to happen, the reaction has to happen at constant pressure. Enthalpy and internal energy are very similar to each other, but you do have to remember the equations involved for both of these variables. Delta E is Q plus W, but for delta H, if that reaction is happening under constant pressure, then you're looking only at Q because the W cancels out. So here's a question relating the two entities, enthalpy and internal energy. We have 1 mole of butane burning at constant pressure, and it produces 2,658 kilojoules of heat and does 3 kilojoules of work. What are the values of delta H and delta E for the combustion of 1 mole of butane? So pause this video, figure out what these two values are based on the equations and the sign designations from before. And when you're ready for the answer, click play. Here's our answer, letter C. So let's take a look at what we have here. This reaction produced 2,658 kilojoules of heat. So because this is at constant pressure, our delta H is going to equal Q. And our Q here is going to be negative because our system produced heat. So automatically we're going to eliminate choice D. Now for delta E. Don't forget this equation. Okay, delta E equals Q plus W. We plug in our values. We already know that Q is negative. And now W is negative 3 kilojoules because our system did the work. Now when you add those negative values together, you should get negative 2,661 kilojoules, with our answer being letter C. Okay, so you might have heard these two terms before, exothermic and endothermic reactions. Okay, when delta H is negative, we already know that Q would then be negative, so heat is being released from the system. This is an exothermic reaction. If heat is being absorbed, so that'll be a positive Q, and so then a positive delta H, that would be an endothermic reaction. So students get confused sometimes with endothermic and exothermic reactions because they forget that the reactions are the system. So if you come across a cold pack, okay, so for this one, it contains ammonium nitrate. So like when that dissolves in water, that is an endothermic process. It needs heat. It needs heat in order to move forward in the reaction. So the reason why it feels cold to you is because the reaction is taking heat from your body. You are the surroundings. The reaction is the system. So when you see that a reaction is endothermic, the reaction is the system. The same thing goes with a combustion reaction, okay, with fire or anything else that releases heat. The system is the reaction. You would feel the heat because you are part of the surroundings. You would be absorbing the heat, so you would feel hot. Now, keeping that in mind, let's take a look at these processes and figure out if they are endothermic or exothermic and indicate the sign of the delta H. So with sweat evaporating from the skin, sweat is a liquid and it's undergoing evaporation. So it's starting off as a liquid, turning into a gas. So just by that should tell you that it's endothermic because heat is needed for the sweat to evaporate. Okay, so letter A is an endothermic reaction with a positive delta H sign. Okay, now water freezing, letter B. Water is a liquid. We're trying to turn it into a solid. So that means we have to take away heat. Heat has to be removed as a product. So in that case, water freezing is an exothermic process. So the sign there is going to be negative for delta H. Okay, now wood burning in a fire. The wood burning, think of combustion. That is the reaction, that is the system. So don't get confused here. You're probably going to picture yourself in front of a fire. You feel the heat, so you might think that that's endothermic. That's not true. Here we are saying that the reaction is the system. You would then be part of the surroundings. So for wood burning in a fire, that would be an exothermic reaction with a negative delta H. Again, you are part of the surrounding, so you would feel the heat that's being released. You are absorbing the heat that's being released. Okay, so now try these three out. Work it out, talk it out, write it out if you have to. Pause the video so that you'd have time to figure everything out. When you're ready for the answers, click play. Okay, here we go. An ice cube melting. The ice cube is the system. It's going from solid to liquid. That's an endothermic process, so the sign has to be positive for delta H. Letter B, that's also a positive delta H. It's an endothermic reaction. Again, it's a liquid nail polish, evaporating to a gas. And then letter C, it's a negative delta H because we have something burning again. Gasoline is burning. That is the system. So with any combustion, that is an exothermic reaction, so we have a negative delta H. So let's take a look at endothermic and exothermic reactions in terms of bonds, the bonds that are found in our reactants and products. So in any reaction, whether it's endo or exothermic, bonds that are in the reactants are all going to break. And new bonds are going to form so that we can make products. So now, what happens in an exothermic reaction? Okay, so here's our exothermic reaction. Our reactants are going to have a higher potential energy compared to our products. So now what happens when we do final minus initial? When we do like a delta E or like a delta H, whatever the case is, that extra energy is going to be released as heat. Okay? That extra energy is going to be released as heat. The products of the reaction have less chemical potential energy than the reactants. So now what if we flip it around and we have an endothermic reaction? Again, with any reaction, whatever bonds exist in the reactant side, they're all going to break. And new bonds are going to form so that we can form products. That is going to be the same as in our exothermic reaction. What's going to be different? The potential energies of the reactants and the products. So with an endothermic reaction, heat is needed. Heat is needed in order for the reaction to move forward. Okay, in order to form A, we have to have B, but it doesn't have enough energy to create A. So it's going to need to take energy from the surroundings in order for the reaction to proceed. So heat is being taken away from the surroundings. That means the temperature of the surroundings is going to drop. The temperature of the surroundings is going to drop. That's why for those cold packs, that's why you feel it as cold, because the chemical reaction is taking heat from your hand. Okay, so here's a question that'll test your understanding. We have an endothermic reaction occurring in a flask. What happens to the temperature of the flask? Pause this, think it through. When you're ready for the answer, click play. Okay, so the answer here is that the temperature of the flask would fall. The temperature of the flask would fall. Remember that the reaction, the endothermic reaction, is the system. Everything else would be the surroundings. Another way to think of it is pretend that you have a cold pack or an ice cube in your hand. Okay, the cold pack or the ice cube, that would be the reaction. Those things would be the system. The flask and your hand, they would be part of the surroundings. So if you have an ice cube in your hand, the ice cube is experiencing an endothermic reaction because it's going to melt. You feel the ice cube as cold. So with the flask, it's the same idea. The temperature of the flask is going to fall. So with enthalpy, you have to realize that it's energy per mole. So this is an extensive property, and that just means that the amount of substance actually matters. So here we have a thermochemical equation. Okay, it's a balance equation along with a delta H value for it. So when you're reading this, you have to take into account the molar coefficients found in the balance equation. So if you have 1 mole of C3H8 gas and an abundant amount of O2 gas, then this reaction is going to produce 2044 kilojoules of heat. Okay, same thing goes with the O2. If you only have 5 moles of O2 gas and an abundant amount of C3H8, you're still going to produce the same amount of heat, 2044 kilojoules. Now, what happens if we multiply this entire balance equation by a factor of 2? So now our new molar coefficients would be 2, 10, 6, and 8. What would happen to our delta H? We'd also have to multiply it by 2. Okay, so whatever factor you use to multiply the balanced equation, you have to use the same factor for the delta H. So this would then be negative 4,088 kilojoules. Okay, so let's see if you understood the previous slide. We have a thermochemical equation. Our delta H for the reaction is negative 51.0 joules. What is the heat associated with the reaction of 6 moles of A? Do the math. You could probably do it in your head. When you're ready, continue on with the video. Okay, here it is. The answer is letter C. Let's take a look at the work. All you're doing is just unit conversion. Okay, we have 6 moles of A. We want the heat, so we have to change our unit from moles of A to joules. So this is where we get our conversion factor. Okay, we have our delta H value. Don't forget about the sign. And we need the molar coefficient of A. So here in our balance equation, it's 2. So when we do the math, we cancel out the 2, and with the 6, we turn it into 3, so we have negative 153 joules as our answer. Okay, so here's our thermochemical equation, same as the one as a couple of slides ago. Here we have a liquid propane gas tank that has 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. Okay, again, here's our thermochemical equation. We have our values. We need to figure out Q. All right, so here are some conversion factors that we would need. We'd have to convert kilograms to grams. Here's our molar mass of propane. And here's our conversion factor going from kilojoules to moles of propane. So you can see here that all we're doing is unit conversion. We're starting off with kilograms of propane, then turning it into grams. We take that value and divide it by the molar mass of propane, and then use our conversion factor with the delta H that was given to us. Okay, when all the units cancel out and we're left with kilojoules, then plug everything into your calculator. That's the best way for you to save time and make sure that your setup is correct. Cancel out all the units first to make sure that you have kilojoules, then plug in your values so that you would get negative 6.12 times 10 to the 5th kilojoules. Okay, and this answer again should make sense. This is negative. We are combusting the propane, and in combustion we are releasing heat. Here's another one for you to try out. Ammonia reacts with oxygen to form an O gas and H2O gas. Calculate the heat in kilojoules with the complete reaction of 155 grams of ammonia. And the molar mass of ammonia is given to you. Always make sure that the equation is balanced before you proceed. Okay, so please press pause, work this out yourself, and when you're ready for the answer, press play. Okay, so again, this is just unit conversion. You're starting off with the mass of NH3, then you're going to convert it to moles, then you're going to convert that to kilojoules. Now watch out for the denominator in that last conversion factor. The 4 moles of NH3 come from the balanced equation. So we would have negative 2,061 kilojoules. Here's one last one. There are 2 things that you would need to figure out. So the first one is the mass of butane in grams that's necessary to produce 1.5 times 10 to the 3rd kilojoules of heat. And then the mass of carbon dioxide produced. So here you have the molar masses for those 2 compounds and the balanced thermochemical equation. Pause right now to answer both of these questions, and when you're ready, click play. Okay, so here's the work to figure out the mass of butane to produce 1.5 times 10 to the 3rd kilojoules. Notice how we have the negative sign here. Do not forget the negative sign, okay? Because heat was being produced. If you forgot this negative sign, then you would have ended up with a negative mass, which is impossible. Okay, so that's one thing that you need to look out for. If you come up with a negative mass, then you must have missed a negative sign somewhere. And here we go for the mass of carbon dioxide. Again, don't forget about the negative sign for the amount of heat that was released from the beginning. Also take note of the number of moles of carbon dioxide, which is found in the balanced thermochemical equation. The coffee cup calorimeter is the second type that you're going to be seeing in this chapter. And usually these are used to measure endothermic and exothermic reactions of aqueous solutions. But you could also use it to, let's say, figure out the specific heat of a metal. So inside this coffee cup calorimeter, you'd have some water, and then you'd introduce a piece of metal that's been heated. You throw it into the water, cover it all up, and measure the temperature difference during the reaction, during the heat transfer. So using this calorimeter isn't always just for aqueous solutions. To figure out the delta H reaction, you have to remember that this device is open to the atmosphere. So at constant pressure, whatever Q reaction you calculate, that is the delta H reaction. And you're going to use Q equals MCAT to figure that out. A couple of more things. The reaction is the system. Okay, the reaction is the system. The solution, so that's the solute and the solvent, that would be considered part of the surroundings. So this is where you would have the QA equals negative QB relationship in terms of heat transfer. Another thing, and the last thing, for delta H reaction, usually that's calculated per mole. So in your chemical reaction, if you're given amounts, you have to figure out the limiting reactant, because then that limiting reactant is going to determine how much products you're going to produce, and hence how much heat is going to be produced. So you have to be careful with that. Here's an example using a coffee cup calorimeter. We have our equation that's already balanced. So we have 0.158 grams of magnesium metal, and it's combined with enough hydrochloric acid to make 100.0 milliliters of solution in a coffee cup calorimeter. The HCl is sufficiently concentrated so that the Mg completely reacts. The temperature of the solution rises from 25.6 degrees Celsius to 32.8 degrees Celsius. Find delta H for the reaction as written. Use 1.00 grams per ml as the density of the solution, and use 4.18 joules per gram Celsius as the specific heat capacity of the solution. Okay, so there are a couple of things that you have to take note here. You don't have to worry about figuring out which one is the limiting reactant, because they tell you that there's enough HCl so that the magnesium completely reacts. So in terms of finding delta H per mole of reactant, you just have to convert the magnesium, the grams of magnesium, to moles. Okay. Also, this density for the solution and the specific heat for the solution, those are the same as pure water. So they're making, this problem easier for you to calculate using those values. All right, so here are our variables with our known values. We're trying to find delta H reaction. We need to use Q equals MCAT so that we can figure out the heat of the solution. But we need Q reaction in order to figure out delta H reaction. Okay, and also delta H reaction is based on the number of moles, so we have to convert grams of magnesium to moles of magnesium. Okay, so our first step in using Q equals MCAT is to convert our volume to grams. And we have to do that by using the density that was given. Then we figure out delta T, which is final minus initial temperature. Now we have all our values to use the Q equals MCAT equation. So Q solution is 3.0 times 10 to the third joules. We need to figure out Q reaction, which is just Q solution, but opposite in sign, so negative 3.0 times 10 to the third joules. And now we have everything we need to determine delta H reaction. Again, this denominator looks a little bit complicated, but really it's just the conversion of grams of magnesium to moles of magnesium. So we would have negative 4.6 times 10 to the fifth joules per mole of magnesium. Okay, magnesium is, technically the limiting reactant here, so that determines how much product would be created. And here is our thermochemical equation. Here's another problem for you to solve. This time, instead of magnesium, we have silver nitrate being introduced to hydrochloric acid. So now we have 50.0 milliliters of 0.10 molar AgNO3, and it's combined with 50.0 milliliters of 0.100 molar HCl. The temperature change from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate delta H for the reaction. Okay, so this is technically a limiting reactant problem because you're given amounts of the reactants, but you're not given them directly. Okay, so just to give you a hint, you have volume and you have molarity. So think about what you learned in Chemistry 101 in terms of volume and molarity. Pause this video, work it out, and when you're ready for everything, click play. Okay, so the whole idea here is to use the molarity equation to figure out how many moles of each reactant you have. So after you do that, you should have found that for both silver nitrate and hydrochloric acid, there are 5.00 times 10 to negative third moles. So they are going to completely react with each other. Nothing is going to be left over. Okay, so when we're trying to figure out delta H reaction, we're going to use this amount of moles in our calculation. Okay, I'm going to use Q equals MCAT because we're using the values for the solution. So in this case, the 4.18, that would be the specific heat for the solution. That means we're finding Q solution. All right, this 1.00 times 10 to the second grams, that was figured out by combining the volumes of our two reactants to get 100.0 mLs, and then using the density to convert the volume to grams. So that's how we got this 100 grams. Okay, so Q solution ends up being 338.58 joules, but we need Q reaction, so we negate that answer, that previous answer. And then we divide everything out. So again, we're using the moles that we calculated before. so that we can get negative 6.77 times 10 to the fourth joules per mole. Here's a question that'll get you thinking about bomb calorimeters and coffee cup calorimeters. In both of them, we have the same reaction with the same amount of reactant. In one of the calorimeters, the Q reaction is negative 12.5 kilojoules, but in the other, it's negative 11.8 kilojoules. Which one was obtained in the bomb calorimeter? And here we have to make the assumption that the reaction had a positive delta V in the coffee cup calorimeter. So the answer to this is letter A. The one with the larger magnitude of Q was obtained in the bomb calorimeter. So just to review, delta E equals Q plus W. But if we're at constant volume, which is the case for the bomb calorimeter, then we're going to cross out the W portion of this equation. So whatever heat was released from the reaction is going to be the delta E for the reaction. Now for the coffee cup, work was actually involved because it says to assume that there was a positive delta V in the coffee cup calorimeter. So part of that energy that was released in the coffee cup, some of that was used to do that delta V work. So we can't cross out W in this case. So the one with the smaller magnitude for heat, that's for the coffee cup calorimeter. Okay, so remember what I said, that the amount of the reactants matter in terms of delta H. We need to know how many moles we're dealing with so that we know how much heat is being released or being absorbed depending on the type of reaction. So this part of the slide here, I've went over a little bit. If we had to multiply our original equation by some factor, in this case a factor of 2, then all our molar coefficients would change. If we have a thermochemical reaction, we have to do the same thing for delta H. We have to multiply it by the same factor. Also, if we have to reverse our original reaction, okay, the products become reactants, reactants become products, we have to do the same thing for delta H. Only this time we're going to be changing the sign. That's like saying 5 minus 2 is 3. Well, what's 2 minus 5? Negative 3. We're just changing the sign here. Okay, so those manipulations that you saw in the last slide, they're important in what's called Hess's law. When you see a chemical equation, you don't know how many steps it took to get to that equation. It could have been just 1 step, or maybe 5 steps, or 20 steps. The whole idea with Hess's law is that if you take a series of steps, a series of chemical reactions, and add them together, you would end up with an overall reaction. You're going to do the same thing with all the delta H values for each of those steps. When you add them together, you'll come up with an overall delta H reaction. All right, so let's take a look at this question here, dealing with Hess's law. Consider the following chemical equation, thermochemical equation. We've got 2A plus B yields C. What is the delta H reaction for 2C yielding 4A plus 2B? Pause this for a moment, think it through, and when you're ready for the answer, click play. All right, so the answer to this question is letter D, negative 244 joules. Hopefully you were able to see that this reaction was reversed. The product became the reactant, the reactants became the products. So because of that, we would have to change the sign here to negative 122 joules. But the original equation was also multiplied by a factor of 2. So we have to do the same thing to delta H reaction. Multiply 2 by negative 122 joules to get letter D. Here's another Hess's law problem. We need to figure out the delta H reaction for this balanced equation. And we could see here that there are 3 steps needed to get to this overall reaction, and the delta H's that go along with each step. All right, so we have to figure out how we're going to manipulate each of these 3 steps. We might not have to manipulate all of them, but we have to take a look at all 3 just to make sure. So first thing that you should do is see where you would have to reverse any reaction. Okay, so let's take a look at this first step here. The compound that sticks out right away is the propane. I could see here in the first step that it's a reactant, but in the overall reaction, it's a product. So I would have to reverse this first step. I don't see it anywhere else, so I don't have to multiply it by some factor. This is 1 mole of propane, this is 1 mole of propane, so for the first step, all I got to do is just reverse it. Now the second step. Okay, I'm comparing the second step with the overall, and I see carbon. It's on the reactant side. It's also on the reactant side in the overall reaction. The only difference is there are 3 moles of carbon in the overall, but only 1 in the second step. So what we need to do here is multiply the whole second step by a factor of 3. Now let's take a look at the third step. Okay, so I see 2 moles of H2 gas on the reactant side. I see 4 moles of H2 gas on the reactant side in the overall equation. So what I need to do here for the third step is just multiply by 2. Okay, we're not going to do anything with the delta H's yet. We have to make sure that what we did here with the manipulations, we have to make sure that what we did was correct. So now we have to apply those manipulations to each step. And you could see that I already did that here. I reversed the first step, I multiplied the second step by 3, and I multiplied the third step by 2. Now with Hess's law, the whole idea there is to add up everything so that we can get the overall equation. So what that means is we're going to add up all of these reactants, put them to one side, add up all the products, put them to one side. An easier way to do that is to cancel out similar terms. Cancel out the same terms, really. So I could see that there are 3 moles of carbon dioxide gas on the reactant side, and there are 3 moles of carbon dioxide gas on the product side. You can cross them completely out if they are the same species, the same phase, and the same amounts. Okay? We're going to do the same thing with the 4 moles of H2O gas. We see it on the reactant side and on the product side. We have 3 moles of O2 gas on the reactant side. On the product side, we have 5. You could still cross them out, but you'd have to write a number 2 here because that's how many moles of O2 gas would be left over if you only crossed out 3 moles on the reactant side. But look, we also have 2 moles of O2 on the reactant side, so in the end we don't have any moles of O2 gas. Okay, so now let's take a look at what we're left with since we're able to cancel out everything we could. The equation that we have after we added all the reactants and products together is the same as our original overall reaction. So once you check that off, now you can manipulate the delta H values. So the overall delta H reaction would be negative 105 kilojoules. Here's another one for you to try out. We have our overall balanced equation. We needed 3 steps to get to there. You have to figure out the overall delta H for this reaction. So take a moment, multiply things out if you have to, reverse things. You might not need to manipulate all of them, but definitely take a look at each step. So pause this, and when you're ready for the answer, click play. Okay, so this is what we needed to do. For this first step, we had to reverse it and multiply by a factor of 1/2, or divide by 2, same difference. For the second step, we didn't need to do anything. Okay, we have NO gas on the product side. We also have NO gas on the product side in our overall reaction. For the third step, you had to multiply by 1/2. Okay, so I'll let you work out these steps with these manipulations just so you could see it for yourself and try it out for yourself. You'll see that in the end it will work. You'll come up with the overall reaction. So then you're going to go ahead and do the same thing for the delta H's for each step. And you'll come up with, for the overall, positive 157.6 kilojoules. Okay, here's the last Hess's law problem that we have. We have 2 steps this time, and you still need to figure out the delta H for the overall reaction. So press pause, work this out yourself, and when you're ready for the answer, click play. Okay, so here we go. This is what you needed to do. For the first step, you needed to multiply by 3/2. That's all you needed to do. You're not reversing anything for the first step. You're just multiplying by 3/2. For the second reaction, you're reversing it and also multiplying by 1/2. When you change these steps based on our manipulations, you're going to see that you're going to come up with the overall reaction. So then you're going to go ahead and do the same thing with each of the delta H's. So then in the end, when you add those 2 delta H's together, you would get overall negative 868.1 kilojoules. So at this point, we have 2 approaches in calculating delta H. One is through calorimetry with bomb calorimeters and coffee cup calorimeters. The other one is through Hess's law, when we're combining a certain number of steps to get an overall reaction. The problem with those two approaches is that we don't know the conditions that were set in calculating those delta H values. We don't know if the pressure was 1 atm, 7.5, like the concentrations of the aqueous solutions. We have no idea what they are, or they could even vary. So with those two approaches, it would be really hard to compare the delta H values with other reactions. So this is why we have this third approach here, and that's measuring the delta H values under a standard set of conditions. So you'll know if a delta H value was measured under standard conditions when you see this degree sign here. You would read that as delta H naught, like naughty. Okay, when you see this symbol, then you'll know that, if when you're dealing with a gas, that was measured at 1 atm. For any solutions, the concentration would be 1 molar. If temperature is involved, we're looking at 25 degrees Celsius. Using these standard set of conditions would make it easier to compare different delta H values of different reactions. Here's another different notation for delta H. This would be the standard enthalpy of formation with this F subscript here. In this reaction, you're only forming 1 mole of product, only 1 mole. And the reactants that are involved are the constituent elements that would make up that compound. Okay, we'll go through a couple of examples so that you can understand this better. But before we do that, you have to understand that some of these values, these delta H values, would be 0 kilojoules per mole. And that's only dealing with pure elements in their standard states. So this is just a small portion of tabulated delta H naught values. You have a more complete version in your textbook, and it's in Appendix 2B in the back of your textbook. It'll list, I don't even know, like hundreds of different substances with their delta H values. So don't just go by table 7.5. Look at Appendix 2B in the back of your textbook. Okay, so now, do you have to memorize everything that's on here? Yes and no. No, because, it's just too many to memorize. What you do have to know are the ones that have a 0 value for delta H naught. Okay, so let's take a look at calcium. Calcium is a metal. It's a solid. It's a solid at room temperature. So this is an element in its standard state. So it would have a delta H naught value of 0. Let's take a look at chlorine. Here we have chlorine gas, diatomic. It's in its standard state. Take a look at the delta H value. Moving over to silver. It's a metal. It's going to be solid at room temperature. This is in its standard state. It's got a delta H value of 0. Okay. Also, the phase matters here. Let's take a look at H2O. We have H2O gas and H2O liquid. Their delta H values are different. So when you're using this table or the appendix, you have to be careful of the phase. So also take a look at the balanced chemical equation that you're working with. You have to pay attention to the phase so that you know to use the correct delta H naught value. Okay, so this I mentioned already. Make sure you take a look at Appendix 2B to find whatever delta H value you need for the compound that you're looking for. With these formation reactions, remember, you're only making 1 mole of a product. So that could mean that you would need fractions for the coefficients for the reactants. So here's a formation reaction example for carbon monoxide. It's a gas. We only want to form 1 mole of it. And it's going to be formed by its constituent elements. So that's why we have carbon and oxygen separated. Okay, now we need these elements in their standard states. So for carbon, it's graphite, and it's a solid. For oxygen, you should know that it's a diatomic gas, so we have O2 here. Now the equation has to be balanced, but we have to keep the compound as 1 mole. So in order to do that, we have to put in a 1/2 coefficient for the O2 gas. So please remember this. For any formation reaction, you're only forming 1 mole of product. To balance out the equation, you might have to put in fractions on the reactant side. So here are 2 products that you would have to write the equations for equations for formation. You'd also have to write the delta H naught values for each equation. So let's go through the first one together. MgCO3 solid. Okay, remember we are only forming 1 mole of that product, and our reactants are going to be elements in their standard states. So we're going to have magnesium, carbon, and oxygen. Okay, magnesium is a metal, so it's going to be a solid. We already know about carbon graphite and O2 gas. Okay, you should see here right away that the equation is not balanced, but you have to remember we are only forming 1 mole of product. Okay, so the only coefficient that we would need would be for the O2 gas, which is 3/2. And then, after you look at the values found in Appendix 2B, you'll see that the delta H naught formation for this reaction is negative 1095.8 kilojoules per mole. Okay, here's the other one with glucose. You're only forming 1 mole of the glucose. We have 3 reactants here. We got carbon graphite, H2 gas, and O2 gas. We're going to balance the equation. I feel like this one is more straightforward. We got whole numbers here. We still have just 1 mole of product, 1 mole of glucose. And after looking up the delta H values in Appendix 2B, we would have negative 1,273.3 kilojoules per mole. Here's another equation that you would need for delta H naught. So it involves the summation of all the delta H values for the products and the summation of all the delta H values for the reactants. This Greek symbol here is sigma. That means sum. So that's where we're adding up all the values for products and the reactants. We still have our delta sign. So it'll be products minus reactants. final minus initial, like always. This N here, that N represents the molar coefficient for that particular product or reactant. Okay, you'll understand this better when we go through a problem together. And we're still going to need the delta H values found in Appendix 2B. Okay, here's our first problem. We need to figure out the delta H reaction using standard enthalpies found in Appendix 2B. We have our balance equation here. Okay, we're going to use our delta H naught reaction with our summation of products and reactants. Okay, here's our balance equation again. And the delta H values that we would need. Notice again, O2 gas has a delta H naught value of 0. Okay, so we're going to be using this overall equation again. Summation of products minus summation of reactants. And you can see how the molar coefficients are being applied here. For NO gas, we have 4 moles of it. So we're going to have to include that in our equation. Okay, the delta H value for NO gas is positive 91.3. We have to remember to multiply that by the 4 moles based on the balance equation. And then you're going to do the same thing for all the other reactants and products. Okay, once you do that, your final answer should be negative 902.0 kilojoules. Okay, so you could see that the answer is negative, so this is an exothermic reaction. We have another reaction here. Aluminum solid reacting with iron oxide. And it says that it's highly exothermic. So our delta H reaction better be a negative. Okay, that's your check there. Okay, you're still going to use the standard enthalpies found in Appendix 2B. So go ahead and pause this, do the work to figure out delta H for the reaction, and then click play when you're ready for the answer. Okay, we're going to use our summation reaction again. Summation of products minus summation of reactants. Okay, when we expand that general equation, remember to add the molar coefficients. Okay, here are our values. If you're really good at this now and you could pick out which compounds or which species are in their standard states, then you don't have to include them in your calculation. So for iron solid, that's in its standard state, it's going to have a delta H value of 0 kilojoules, so you don't even have to put that in there. 2 times 0 is 0. Same thing for aluminum solid. It's in its standard state, so its delta H would be 0. When you do all the math, you should have negative 851.5 kilojoules. Just to sum everything up, here are the 3 different ways for you to calculate delta H. Here specifically on this slide, this is enthalpy of formation. You could see the F subscript here. So we're only forming 1 mole of product. And don't forget, in order to balance the equation, you might have to put in a fraction as a coefficient for the reactants. This next way you could see is Hess's law. We have our 3 different steps. We cancel out a couple of the species so that we can get our overall reaction, just like what we have on top here. This is the combustion of methane. So when we do that, we would also have to combine the delta H values for each step to get our overall delta H value. And this last way we just looked at, it's the summation of products minus summation of reactants equation. It looks a little bit messy, but I feel like this is, very straightforward. You're just plugging in numbers, multiplying, basic arithmetic here. You just have to remember, and this is what a lot of students go wrong, they forget to multiply by the molar coefficients. This next problem here sort of combines everything that we've learned so far. There are several steps that you have to take to answer the 2 questions that they ask for. So here they're saying that in a city, the 100,000 people would use about 1.0 times 10 to 11 kilojoules of energy per day. We're going to pretend that all that energy comes from liquid octane, the combustion of liquid octane, and it forms gaseous water and gaseous carbon dioxide. We're going to use the standard enthalpies of formation to calculate delta H naught reaction for the combustion of octane. That's 1. And then determine how many kilograms of octane would be necessary to provide this amount of energy. So that's the second thing that we have to figure out. Okay, we write out what we know. We have to find delta H reaction and also the kilograms of octane. Okay, we're going to use this delta H reaction, summation of products minus summation of reactants. We need to go from moles of octane to grams of octane at some point. So that's where we need its molar mass. The question asks for kilograms of octane, so we would need that conversion factor. And this is our balanced equation that we're going to use. If you balance this out yourself and you see that you have different coefficients, it could be fine. The book just wanted the number of moles of octane to be 1, just to make calculation easier. So if you had instead 2, 25, 16, and then 18, that's still okay. But you'd have to be careful that you do have 2 moles of octane. So you might have to do like an extra calculation there. Okay, here's our balance equation again, along with the delta H naught values that are needed and that were obtained from Appendix 2B. And this is the work that you would need to have in order to calculate delta H reaction. Okay, again, don't forget about the molar coefficients. So you'd end up having, as an answer, negative 5,074.1 kilojoules. So we got our first answer, our delta H for the reaction. Now we need to figure out how many kilograms of octane were needed. So we would use that delta H value. We'd use that delta H value and create a conversion factor based on the number of moles that were in the balance equation. So this was that extra step that I was talking about. If in your balance equation you had 2 moles of octane, then you would have a different number here for delta H. It'll be 2 times this number. Okay, so I mean that's fine. You just have to be careful when you're incorporating that into your calculation here, you'd have to have 2 moles of octane, and then 2 times this number and put it in the denominator. Okay, so that's the extra thing that you had to watch out for. Okay, so because we have 1 mole here, we could just use the delta H value that we have as is. And right, so up to here we would have moles of octane going from kilojoules to moles. Then we'd multiply by the molar mass of octane to get grams, and then divide by 1,000 so that we can get kilograms of octane. So our final answer here would be 2.3 times 10 to the 6th kilograms. Right, make sure that the answer is positive. Okay, if you ended up with a negative mass, then you know that you did something wrong. You must have forgotten one of the negative signs here in the calculation. Okay, so you've seen this equation before. This is the reaction found in chemical hand warmers. It is an exothermic reaction, so you should write the word heat here on the product side. This question is asking you to calculate delta H reaction and how much heat is produced from a hand warmer that has 15.0 grams of iron powder. So pause this, take a few moments to figure this out, and when you're ready, press play. Okay, we're still going to need this reaction here, summation of products minus summation of reactants. Okay, don't forget about the molar coefficients. The only value from Appendix 2B that you really needed was for the iron oxide. Okay, your 2 reactants, they would have a delta H value of 0. So the delta H reaction here is negative 1,648.4 kilojoules. And that should make sense because this is the reaction for a chemical hand warmer. Heat is supposed to be released. That's why we have a negative value. Now, to figure out how much heat was produced from 15 grams of iron, well, that's where you would need the molar mass of iron, 55.85. So going from grams to moles, you'd have to divide that molar mass value. Then you're going to multiply by the conversion factor based on our delta H and our balance equation. So don't forget that we have 4 moles of iron in our balance equation. So if you have 15 grams of iron, you're going to end up with negative 111 kilojoules of heat. So for the last several slides, we're going to talk about energy usage and its effect on the environment. Everyone here who's listening should know that climate change is real. Because we're using so much fossil fuels, the products from those chemical reactions is affecting our climate worldwide. So here we have 3 different combustion reactions. Okay, here we have propane. It produces the most heat, but unfortunately, it produces the most moles of carbon dioxide gas. And you'll see later that it's important to have this gas in our atmosphere, but too much is going to be detrimental to the climate and our world. You can see here that we are using fossil fuels mostly in our energy consumption. Over the years, into the future, we're going to have to decrease this usage and increase the amount of renewable energy available to us. Oh, we can't just worry about climate change. We also have to take into consideration any impurities that were added to these fossil fuels that we're using. So depending on the fuel, over time, we can experience damage from acid rain and also air pollution. If we breathe in too many of these impurities and other pollutants in the air, then it's going to affect our health. With the acid rain, buildings and cities, plant life in rural areas, they could all be destroyed from the acid rain. So carbon dioxide is a greenhouse gas. We do need it in our atmosphere so that certain radiation coming from the sun can be filtered out. It's one of the ways the Earth can stay warm, but we can't have too much of it. And because of the Industrial Revolution and us using machines, whether they're big or small, the temperature of the global air has been increasing in the past 100 years. And that's not going to be good for our climate. You could see this now where there are some areas where they're just too dry. Normally, plant life would flourish, animal life would flourish, but because there isn't enough rain, those areas would be completely dry and arid. Or you could see areas where it's normally hot, like all year round, and then all of a sudden there would be crazy snowstorms. Or even here, like in the Northeast, yeah, we would get hurricanes every season, but too often we're getting the really strong superstorm hurricanes like every several years. So those are the changes that we could see based on our usage of fossil fuels. Our hope for the future is to shift towards renewable energy. So that's using solar power, wind power. A lot of people are really advocating for nuclear power. There are some dangers there. I can understand people's concern for nuclear power, but really the whole idea is to shift away from using fossil fuels. And hopefully there are some of you out there that can really take charge of this, go into this type of science so that we can still live in our world, without destroying it. In this problem, we're going to take a look at how much heat in kilojoules is released per kilogram of carbon dioxide produced. And specifically, we're going to look at combustion reactions of carbon, natural gas, and octane. Okay, so the math is going to be what you've been doing before, except now we're actually applying it to a real-world issue. So here are the three reactions for carbon solid, natural gas, which is methane, and octane. Okay, these equations are already balanced, and we have the delta H reactions for all three. Okay, so we're going to need the molar mass for carbon dioxide so that we can convert the mass of CO2 to moles of CO2. We're also going to need the conversion factor going from grams to kilograms. Then our next conversion factor would be kilojoules per mole of whatever fuel we're looking at. So remember, we have 3 different fossil fuels that we're analyzing. Okay, so these values we already got from our thermochemical equation. The moles of carbon dioxide produced and the delta H values associated with them. So then all we got to do next is convert the kilograms of carbon dioxide to moles of carbon dioxide. Don't forget we're going to use the molar mass of it. Then we're going to take these moles, because this is for 1 kilogram of carbon dioxide, and see how much energy is released based on the delta H values from our 3 different fossil fuels. Okay, so we have those calculations for just regular carbon, for methane, and for octane. And we could see that octane produces the most heat for every kilogram of carbon dioxide produced. This is the last problem that we're going to look at in this chapter, again dealing with fossil fuels. So what mass of carbon dioxide in kilograms does the combustion of a 15-gallon tank of gasoline release into the atmosphere? Assume the gasoline is pure octane and it has a density of 0.70 grams per ml. And we got the molar masses of octane and carbon dioxide. Here's our thermochemical equation. So let's just jump right into it. Okay, so one of the first things that you would have to do is convert the gallons, the 15 gallons of octane, into liters. We're going to have to get metric here. Okay, once we do that, we convert our liters to milliliters and then use density to get the mass of gasoline. Okay, so for those of you that are just like a little bit confused here, the 15 gallons, yeah, that's volume, but we need to know the mass of that volume. So using density, we have 3.974 times 10 to the 4th grams of octane. Okay, then we use that mass of octane, convert that to moles. This is stoichiometry now. We're converting it to moles of octane. Then we use our balance equation to convert it to moles of carbon dioxide, then to grams of carbon dioxide, and then kilograms of carbon dioxide. So we end up with 122 kilograms of carbon dioxide. This is stoichiometry. You're turning one substance into another substance using a balance equation.